welcome to the fourth installment of the GDS tutorial series. This is just a reminder that the recording of today's tutorial will be posted on YouTube. And while we encourage you to unmute at any time and ask questions, if you're not comfortable with your video or your voice being on the YouTube channel, now would be a good time to make sure you're muted and your camera's off. We ask that you do remain muted throughout the entire tutorial unless you have a question, just to not distract any of the other participants. And so before I pass it over to Dr. Trevor Rhone, who will be giving the tutorial today, I wanted to do a few announcements. So if you have any suggestions for future topics or speakers for the tutorial series, please feel free to email them to me. For the QR codes on the bottom of the screen currently, if you have any feedback for the tutorial series, either things you want to see us do in the future, things you think we should change or improve on, please use that QR code on the left and let us know what we can change. If you want to find the materials for today's tutorial, please scan the QR code in the middle. That will take you to a GitHub page, which has the materials for every tutorial in our series so far, and all you'll need to do is go to the folder that starts with today's date to find the materials that we'll be going over today. And if you're not already a member of GDS, if you scan the QR code on the right side of the screen, you'll be taken to the page where you can sign up for GDS. The next tutorial in our series will be on May 25th at 1 p.m. And it'll be by Dr. Cormac Tower of the University of Texas at Austin. And he'll talk about accessing training data through materials data's APIs. And if you're interested in attending that talk, you can register through the same link you used to get the Zoom link for today's talk. If you want to view any of the recordings of the past 3 tutorials, you can view them either on the left-hand QR code on the GDS Engage page, or on the right-hand QR code for the YouTube channel. Yes, Igor.
Sorry, did you say May 25? Is that a
May
Sunday?
25. Yes.
Oh, Sunday. Okay.
Oh, sorry. That not the Friday?
No, Friday will be 23.
All right, 23 then. That's not right. 23. 2 Fridays from now.
Okay, thank you.
Thank you. Thank you for pointing that out. And so I'll put these here as well. If you do scan the QR code on the left for the Engage page, that also will show you the schedule for all of our currently booked tutorials in the future, along with the registration links for each. And so with that, I will stop sharing, and I will turn it over to Dr. Rhone, who will be giving us a talk on unsupervised learning.
Thanks so much, Julie. I'm Trevor Rhone. Let me share my screen here. Everything is looking okay?
You're good?
Wonderful. Let's see. Try to get this box out of the way. Great. Okay, so my name is Trevor David Rhone. I'm an assistant professor at Rensselaer Polytechnic Institute in upstate New York. The title of today's talk or seminar tutorial is Introduction to Unsupervised Machine Learning. Okay, so for some housekeeping before we get started, you'll need to navigate to the GitHub page to get the Google Colab notebook. And maybe while listening, if you don't already have an API key with Materials Project, you need to get an account with Materials Project to do some of this tutorial. You can get links easily through the QR code to the GitHub page we'll be using on the left here. And on the right, you'll get access to the Materials Project website with which you can use to sign up, get an account, and get an API key. We won't need this for the next, 20 minutes, 30 minutes or so, but it would be useful to get started before we actually need the things. Okay, so segueing into introduction, we go back and forth between presentation mode and hands-on exercises, and feel free to ask questions as they arise. Either unmute your mic or use the chat if you prefer. So advances in materials drive technological innovation is the motivation for why we're doing this, using AI to do materials science research. And traditionally, to gain these advances in materials, one does materials design and discovery. Typically, or traditionally, that's done with serial experiments and first principles or ab initio calculations, which tend to be slow and rather expensive. So in the past, maybe 10 years or so, materials informatics or material science plus machine learning or AI has really become this really important tool that helps accelerate this materials design and materials discovery process. Although it existed for some time, it's only really become mainstream in the past 10 years or 5 to 10 years or so. Of course, it's still an active area of research, and there's still some challenges for materials informatics. One of those challenges, which we'll focus on today, is this lack of labeled data. And I'll describe what that means in a bit when we get into some more details. This is really an exciting time to be doing AI for materials research or for physics research. The Nobel Prize in Physics went to two researchers in AI last fall, to John Hopfield and Geoffrey Hinton, for foundational discoveries and inventions that enable machine learning with artificial neural networks. So it's a really exciting time to be here learning about these things. So welcome, and you're off to some exciting future directions. Okay, so let's start with a machine learning overview and maybe building some vernacular. So this is AI, and machine learning is a subset of AI, although I'll probably use the terms interchangeably. AI, by definition, incorporates machine learning and robotics control, although robotics control is becoming an increasingly important part of the materials science. We'll talk about that today. It intersects with data science, which comprises data mining, databases, data visualization, and statistics. The typical machine learning framework involves three key ingredients in data: descriptors and statistical models. The databases are really coming powerful and plentiful. They didn't really exist 10 years ago, the materials databases with digital access, but there are quite a few of those today, which is really enabling this material informatics workflow. There's also really clever researchers spending their careers building really nice mathematical representations of materials, crystal structures, chemical composition. One of the early ones are shown here, a Coulomb kernel in the bag of bonds representation. And there are many data science tools that exist, which are powerful, free, easily accessible with lots of documentation. These include things like scikit-learn, Google's TensorFlow, and PyTorch, and you'll use some of these tools today. So let's focus a bit on the data. So there's lots of databases, as I pointed out, like Materials Project. We'll use Materials Project today to do some of our tutorial. There's AFlow, MatNavi, provided by NIMS, National Institute for Material Science. I was actually working for NIMS for a few months when I was living in Japan. It's a great place. C2DB, one of my favorite databases that's leveraging 2D materials or comprising 2D materials, OQMD, Nomad, and the ICST, or the Inorganic Crystal Structure Database. And these are just a few. Actually, they're really, more and more popping up every day. And maybe the most recent ones aren't in this list, but it's not an exhaustive list. And there's the second ingredient, these descriptors, which again are descriptions of materials, which may comprise the atomic properties of the constituent chemical elements, or some clever mathematical representation of the crystal structure. An example that's quite simple-minded is, let's say you're studying a set of ionic compounds. You might notice that your elements comprise different columns in the periodic table. So you might use column number for your description of your set of materials. And we'll look at some more sophisticated examples in the exercise, but these are just some nice simple-minded ones. And the third ingredient, which is also quite important, are these statistical models. Some you should be already quite familiar with. There's this linear regression, So if you've done linear regression before, you've done machine learning, where you take some points and you fit a line to those points, and you can make some predictions based on the line that you have. And there's nonlinear models such as decision trees and neural networks. We'll look at neural networks later on, but here are some models in decision trees, which helps you to get an idea of why it's nonlinear. In this case, you have three descriptors: age, student status, and credit card rating. And this decision tree is a classification model, which predicts whether you give somebody a credit card or not. And this simple-minded, funny example is meant to be lighthearted. You ask what's the age of the person. If they're young, then you ask what's their student status. If they're not a student, you don't give them credit card. If they are, then you do. And you can adapt this for also doing regression. And because of this trees is if then in different levels, you have this highly nonlinear learning task. Okay, so the data science comprises data visualization and materials machine learning, where the machine learning is approximating some function f of x, 1 through xn, where the inputs of this function f, which is approximated by some machine learning model, are things that are easily attainable in like a set of a chemical handbook or atomic properties of the constituent elements, something that you'd easily measure, get from a table, or calculate. And it maps out something that's difficult to calculate or difficult to measure, like the magnetic moment for a material, or there's some magnetic properties. So the goal is to learn or quantify some relationship. You can measure it, or you can do some sort of really expensive quantum simulation that typically takes a supercomputer, it takes some time, or you can approximate the relationship with this function and then evaluate the function really quickly on a laptop. And this is a nice advantage of using a machine learning approach. Okay, so a lot of machine learning is supervised, but then there's this unsupervised approach, which is what I'll be focusing on today, which is kind of exciting. So in supervised learning, you have label data. So this could be X1 and X2 or some description of some set of materials. And the circles are whether the material is ferromagnetic, and the X's are where the material is anti-ferromagnetic. And you can paint the points with the circles or the X's, and you kind of then can draw a decision boundary, which is what the model is learning, this decision boundary. And then you can predict whether a new point that falls over here is either ferromagnetic, or if it falls over here, anti-ferromagnetic. That's supervised learning. In unsupervised learning, you have a bunch of points. You still have some mathematical representation of these points. You can make a plot like this. And you might notice that there's some clustering. So you might say, well, maybe there's something similar about these points that you can take advantage of. Maybe these are all anti-ferromagnets, or these are all ferromagnets, or these are all altermagnets, or something like that. And so you can use this unsupervised approach where there's no labels to get insight into your data. We'll be focusing on this right side, unsupervised learning today. So supervised learning, you have a set of measurements, observations that are associated with a response. So a set of measurements X sub I, and these are associated with some response Y sub I, or some label. This could be something that's a result of a calculation or an experimental measurement. And the goal is to predict the response given the observations or the measurements. That's a prediction. Or often what's quite interesting but challenging is to do inference, where you're learning the relationship between the response and the predictors. In unsupervised learning, there's no Y value. You're just learning a relationship between the X bias, the observations, and how they're parameterized. And we're focusing on this in supervised learning today. Okay, in supervised learning, unsupervised learning, there are different things to focus on. There's dimensionality reduction, which you can do using principal component analysis or PCA. This finds some dimensional representation of the observations that explain a good fraction of the variance of the data. I'll explain what that means in a little bit. There's a T-distributed stochastic neighbor embedding, or T-SNE for short, which is doing something similar, but looking at how some point relates to its neighbors in some space. And this is a nonlinear kind of like a dimensional reduction tool, as opposed to PCA, which is linear. There's a clustering, which is finding homogeneous subgroups or clusters of data, which might have some similarity within each cluster and dissimilar between clusters. To do this, you can have various models. We'll talk mostly about k-means clustering today, but there's also hierarchical clustering if you want to investigate that. That's a popular tool for supervised learning. There's associative learning, which is trying to learn patterns in the data and making associated rules. I'll talk more about that in a bit. Popular models for that include the a priori algorithm and the FP growth algorithm. We'll focus on just one of those today, the a priori algorithm. And there's generative models. Hopefully we'll get to this today, which is basically leveraging either variational autoencoders or generative adversarial networks or transformer based on generative models, example like GPT, like as in ChatGPT. We'll focus on this VAEs today. We won't have time to get to the other two. So let's start with clustering. So again, you want to find some subgroups in a data set where you have some set of observations. You want to find those observations are similar within a group and dissimilar with groups that are not in that group or between groups. For example, you can imagine having some data. You want to cluster the data in groups of non-magnetic materials, ferromagnets, and anti-ferromagnets. So what we can try to do using these clustering tools, and in particular algorithms for doing that, are these again k-means clustering and hierarchical clustering. K-means, it's maybe the most simple-minded algorithm. We'll start with that one. So you want to partition your observations into a specified set of clusters. In this algorithm, you have to pick which number of clusters you want to try to use first. And you might want to pick that based on some domain knowledge or guess something and then try different numbers for K and see which one works best. And so in the k-means algorithm, you assign to each observation one cluster. You attempt to minimize some loss function for each of the clusters. W, or W is defined like this, using a kind of Euclidean distance. But this is small when you have points close together, all in the same cluster, not far from each other. And it's large when you have your points within a cluster far from each other. So you tend to have points within a cluster form in some localized set of points as opposed to delocalized points. Looking back to the picture I showed you a bit back here. So k-means would identify these three clusters here, which is easy to do by eye, but maybe not easy to do in some high-dimensional space, by eye in two-dimensional space, but not so easy to do in a high-dimensional space. But easy for the k-means clustering for some n-dimensional space greater than 3 if you have this algorithm working pretty well. So how does it work? You have some points, you initialize your points, your clusters, and then you use an algorithm to minimize your loss function. After the round 2, you might get your first cluster centroid, your center of mass here, another one here. And as you continue, you get a bit better by a little bit, identifying the clusters more clearly. And then when you're done, you more or less end up here in the steady state.
Trevor?
Yep.
There's a question in the chat. What is the parameter you optimize over to identify each cluster?
It's kind of the Euclidean distance. So you try to basically minimize distance between points in each cluster. And it's right here. There are other hyperparameters you can choose, like number of clusters. That could be something you can choose by or vary by picking, say, k equals 2 and running the algorithm, and then seeing how it works, and then p equals 3, running the algorithm and looking at the loss, and by you doing validation, find which k is better. Does that answer your question?
Just to clarify a little bit more. So in the loss function you have here, you say minimize C1 to CK. So what is C1? What's the thing you're minimizing?
It's like this. C1 is basically this first cluster, well, a cluster 1, call it, and C2 would be the second cluster 2, for instance.
So what's a characteristic of C1? What's the expression for it, I suppose?
inspection for C1. You identify
Yeah,
a cluster, and then you just try to minimize it's a collection of points. It's described by some collection of points, and you try to
I see.
minimize the distance between those points.
So you identify the set, basically.
Find a set. I didn't catch what you said.
Sorry, each cluster is a set of points
Yes, that's right.
of observation.
Yep.
Okay.
Yep. Any other questions? Yeah, thanks for asking that. Okay, so now we have a chance to do a hands-on example. So you have a, let's see, let me show you go back to this QR code here. So navigate, if you haven't already, to the, maybe better to do right now, the Google Colab exercise by looking at QR code over here, or typing in the web address here. And then finding that Google Colab notebook. I'll give you a minute to do that, maybe half a minute. On a web address or QR code. And while you're here, you should grab the website for the materials project. You can also find it by Googling materials project and maybe register or sign it. Although we don't need that right now. Okay, so hopefully you managed to get the link. And let's go back to the hands-on bit, which is right. So hopefully everybody's here with the notebook here. And what I like to do is kind of give you some guidance, but I like you to really play with it yourself. So take ownership of your learning and ask lots of questions. And it's not nice if you're working with each other. So maybe send messages over chat. If somebody in the same room with you, talk to them. Okay, so let's go through this. The first part is just pip install the packages that you need. And the first cell, just under the k-means clustering heading, is just gathering some dummy data using some module called make blobs. Okay. And then I like you to just kind of inspect X once you've created your dummy data by printing its shape, maybe printing a few values in X, printing the entire X, the entire set of data. And just to confirm that you have, 300 samples with maybe 2 columns for the 2 features. You do that in this cell. Once you've done that, it should take you a couple seconds. And this part of the code is leveraging your k-means clustering algorithm. Identify clusters, and then plots the results. So in this case, you have you have some graph with feature 1 on the horizontal axis, feature 2 on the vertical axis, and you have a set of points, and there's this X here which labels kind of the centroid or the center mass of the points, and it's also painting the points with different colors representing different clusters. So the algorithm assigns this X here, which is the centroid or the center mass for the set of points, and also assigns the color for the points. So it's pretty easy to look at this and see that there's 3 clusters. But imagine a situation where maybe there's some overlap of the points, or we're not in 2-dimensional space, we're in like a 10th-dimensional space. Identifying clusters in that 10th-dimensional space is a bit more challenging for our human brains to do, but not so difficult for an algorithm like this. One thing you could do, play with it, is to change the number of clusters, for instance, and number of features by tuning the data, dummy data, and the algorithm. And just take a few moments, maybe another 5 minutes or so, just to tune the data set you're using and the k-means clustering algorithm, and see what the result is. So for instance, maybe you can change number of clusters to 2 instead of 3 and see how it works. Change it to 4 instead of 3 and see how it works. then you can manage changing data to having 4 clusters instead of 3 or 10 or whatever you like, and then looking for those clusters in this set of large number of clusters. Just get used to the algorithm. Okay, so we have another 4 minutes for this part of the tutorial. So please feel free to answer questions, ask questions. I'll try to answer them for you as we proceed. Another thing you can do is consider the other questions I'm asking down here. I'll ask one of you to give me your opinion in a few minutes. Okay, do you need more time before we start answering the questions? Say something in the chat or unmute your mic and say yes, need more time. Okay, if not, then I'll ask you, how do we know how to choose K for some unknown data set? In this example, we're a little cheating by setting the number of clusters to be 3, creating or a data set using make blobs. But if you get some data and you really don't know how many clusters there are and they're not pre-specified, how do you figure out which K to choose? Anyone want to volunteer answering the question?
Sorry, I don't understand the question. What do you mean, which K?
You have some data set and you want to search for some clusters which have some similarity within each cluster. How do you choose how many clusters you set in your algorithm? You have to set in advance the K. It should be 2, 3, or 4 before you run K-means clustering. How do you choose that value for K? That's the question. Is it clear?
Oh, okay, I see. Yeah, okay, because we use then clusters in both to generate the data and also to do the clustering. I see. Okay.
Yeah. So for this example, it's a little bit contrived because it should be 3. But let's say you have a data set from your research, for instance, or something you're interested in doing, like analyzing the economy with something that you're passionate about, bunnies or something like that, and making it up. How do you choose your K clusters?
I mean, I guess you can always try it and see what works best.
Okay, absolutely. So that's one approach. Let's try and see what's best. Which number of clusters gives you the lowest loss for, say, a validation data set. Some validation data is some data that's outside the data used to train your model, or some holdout data. And there's one other thing you can do, and I'll answer because we're about out of time for this part of the hands-on exercise. You can use your physical insight or your domain knowledge. So for instance, if I'm doing a study of magnets or materials with long-range magnetic order, and I might have an idea that in my data set, I have ferromagnets and anti-ferromagnets, and maybe materials with no long-range or non-magnets, then I might want to choose 3 classes. And so my K would be 3 in this particular case. If I'm looking at a data set with material with order, long-range order, and not long-range order, then it'll be 2. That's another example. Okay. So are there any questions before we move on?
I have a question about n features. Is that basically the number of dimensions we're doing this in?
Yes, that's right. That's a great question. Yeah. In this case, I think I chose 2. Yeah. And which is easier to plot. But if you had like 10, it's harder to plot that, or impossible, depending on what you want to do. And then this algorithm really becomes something that's useful, because it's hard to just look, as we can do here, and see, oh, there are 3 clusters and they're clearly clustered in 10-dimensional space. It's harder to do that. And your 10-dimensional space is some 10 features of your data set. So it could be the lattice constants, ABC. It could be the volume of the unit cell, that's 4 features. It could be the whether boron occurs in your data set or not by one hot encoding and one new 0. You can kind of add to features like this, and then it can be quite a large number of features in the end. But you still want to find clusters in this space, and how do you do it? It's hard to do by visual inspection, but you can use an algorithm to do it. Yeah, thanks for asking that question. Okay, so now I think we should move on. We go back
Also,
to
Trevor, real quick, there's a question in the chat. What do you do if the dimensionality of the problem is higher or comparable to the number of measurements?
Oh, that's a great question. We're actually going to touch on that a little bit later on. But I can answer that quickly. It's a fantastic question. What you want to do is try to reduce the number of dimensions or features by either doing a feature selection, picking which features are most important and tossing ones are not, using either kind of a validation approach by testing features and looking at which ones are not important, by checking if they're important for increasing R squared score or some sort of score metric. Or you can say, well, if I'm trying to predict the say the price for a home in my real estate data set, and I can guess that maybe the number of trees in the neighborhood or the color of the house doesn't really make a difference. So I'll eliminate those as features, and I'll keep things like number of floors or the square footage of the house. And easier as far as implementation approach goes is just to do like PCA, which we'll talk about, I think, next. So the perfect segue. Talking about PCA, or doing dimensionality reduction on your data, which helps to answer your question. You can do this by exactly what you asked. You have some number of predictors, P, and they're more than your number of data points. So you can create some m-dimensional subspace less than P, which is going to help you to reduce your number of features or effective features. And if it's reduced down to 2 or 3, then you can use this for data visualization. So you can map your 10-dimensional space using this dimensionality reduction technique to 2 or 3-dimensional space and make plots and kind of help to make sense of data using this approach. Tools you can look at are PCA, principal components analysis, T-distributed stochastic neighbor embedding, or TSNE, and autoencoders. We'll focus on PCA and look at some autoencoders, but for another approach, that's what I'm looking for. Not for dimensionalized reduction, but for generative modeling, but we'll touch on that today also. Okay, so PCA is lots of fun. What is PCA? It's a way of summarizing data by mapping to smaller set of variables that collectively explain most of the variance in the data. And that's a bit of a mouthful, but I'll show you an example which hopefully makes that super clear. So you have some set of features, x1 to xp, with no y, no label or associated response. So there's no result for your DFT calculation. You don't have the total energy, or you don't have the magnetic order. There's no y value, just the things that describe the materials, lattice constants, chemical composition, crystal structure, things like that. And what's this useful for? It's a good visualization tool. And as the person asked the question pointed out, it's a good way of producing variables for supervised learning. So you can map your large set of features which is more than your number of data points, to some number of features less than the number of data points by a bit, and then use that for supervised learning. Okay, so PCA is, let's say, take some a data set with 2 dimensions, x1 and x2. In this data set, your first principal components has the component as is some linear combination of x1 and x2, where most of the variance data is described. It's this direction here. Most of the variance is happening along this axis, this first PCA direction. Now, orthogonal to that is your second principal component here. Okay, so you might think, well, that's not terribly interesting. What's the point of doing that? Well, it's maybe more apparent in 3-dimensional space. You have some x1, x2, x3, and you have essentially a pancake where a lot of the variance is happening on this first principal component direction here, second most along here, and almost nothing along this third direction. So if you just projected your new space along PCA1 and PCA2, you can disregard PCA3 and use this to model your data. And this is maybe more useful in like 10-dimensional space. If you have lots of other dimensions which don't have much variance in the data, you can just get rid of those and use your 2 or 3-dimensional space to explain most of the data. So, are there any questions about that? Okay. And this is, again, linking to a question that was asked earlier. Traditionally, statistical methods are designed to have number of features much smaller than the number of data points. So the number of observations n is much larger than the number of features p. That's what your traditional statistical techniques are assuming. But these days, we're having a lot of lots of data. We have Internet of Things, IoT. We have access to things like fancy measurements, which give us a lot of more features to look at. One example, which is maybe taking to the extreme, instead of predicting someone's blood pressure using age, gender, and BMI, you can collect their DNA and look at their DNA mutations or their single nucleotide polymorphisms. That gives you 500,000 features to look at. In a data set of 200, that's really unwieldy. So what you can do is use PCA, although DNA data are important. It's not possible to do your statistical tools with this because you get overfitting. And so you reduce these p dimensional features to m, much less than, say, 200 to do then your machine learning. And one point is, in this case, where p is much bigger than n, number of observations, where your features exceed your number of observations. This is your high dimensional feature space. Okay, so now we get to enjoy doing our second hands-on example on principal component analysis. So spin up your notebooks again. And in the first cell under the principal component analysis heading, you have some make classification function, which again generates some dummy data. And you can choose number of samples, number of features, classes, and so on. Let's keep it like this for the time being. Evaluate your cell. Then you might want to inspect the contents of X. Does it indeed have 300 samples? Are there indeed 10 features or 10 columns? You can print your shape of your X here. You print a few values. What does X look like? Get a sense of what's in the data set. And then you typically transform your data by rescaling it, by subtracting away the mean and dividing by the variance, I believe, before you pass it into your PCA function for principal component analysis. In this example, we're looking for reducing it to 3 principal components. So we set n components equals 3. Then we can fit or data at scale using PCA.fit transform. And the rest is just looking at the result of our principal components. We plot it down here. And in the first plot, we're plotting the first principal component versus the second principal component. We're labeling our data using this color plot, which looks at 3 classes labeled 0, 1, or 2. So if it's dark, it's one class. If it's super light, this is another class. So it's kind of in between, it's a third class. Here's the results. And if you want to plot the first component against the third component, here is the other result. So hopefully you've done that. Here is plotted the explained variance for the first and second principal component, and you have 60% representing that explained variance. So 60% of the variance in the data are explained using the first and second principal component. If you imagine if it were like 95, then you know for sure in the third, fourth, fifth, for instance, component, I think in this data set we had 10 features. They're more or less not varying at all. Maybe they're all constant or they're not varying very much. So you can kind of just toss them out. Okay. So the question I have for you, I'll give you maybe a couple minutes to go through the code and perhaps change the number of dimensions, maybe plot the first or the second principal component versus the third principal component. So you can add to another, to the subplot here, make another plot to another cell. You can also maybe change the color scheme, something that is just solid colors. What else could you do? You can also think about making this instead of 3 to 4 or 5 principal components and see if it helps to give you some insight into data. I mean, these are just dummy data, but you can imagine by inspecting this that there's kind of a cluster here forming, maybe another one here, maybe another one here. So perhaps by reducing this 10-dimensional data set into 3, plotting the first versus second principal component, you gain some insight of what's going on. And I would say also here, but maybe a little less so in my eyes, but well, maybe it's comparable. So play with that. I'll give you a few minutes to do that, and I'll ask you a question in a little while. Also, you can change the data and see how this result changes. Can you capture most of the variance in the first and second principal component? Instead of 60, can you go to 90 or 80? It gets less. If you want to capture explain most of your data, what value should this be? Should it be higher or lower? Think about these things. And feel free to continue asking good questions.
So the 3 colors, like clusters?
Yeah, they're not by design, but I would guess that they look like there's clustering here. So the 3 colors are different classes. In this data set, we've asked it to have 3 different classes. So in this data set, there are 3 different classes for Y, and we're choosing just to color things based on those Y values. And it somehow comes out that it looks like they're clustering, but they don't necessarily have to cluster. One thing you can do for PCA is to help reduce your space, look for clusters to help guide your research. Maybe you reduce your space and do k-means clustering. Just a tool to help to visualize and to analyze using machine learning or other things, other tools, your data. Did I address your question adequately?
So, I mean, this basically comes with telling it to make, I'm just trying to understand what make classification does. We're telling it to make data with 3 classes.
Mm-hmm.
But what does that really mean?
Oh, so let me give it some context. So let's say you're looking at real estate data and your data set has mobile homes, townhouses, and mansions. So in your data set, you have these 3 types of homes: mobile homes, townhouses, and mansions. Really large homes with 4 or 5 stories and 20 bathrooms. And you're trying to classify, given your data, which one is which for some reason, and linked to real estate. And in that case, your number of classes is 3. You can also maybe look at a more physical example. You have a data set where you have ferromagnets, non-magnets, and altermagnets, or maybe if you haven't heard of altermagnets, antiferromagnets. And the goal is to try to analyze data set using PCA. So the first part is this create data. You can feel free to choose this to change this to something else. And the second part is doing PCA and plotting the result. And then we'll discuss how PCA can be useful for analyzing data in a second. So really the goal here is to use PCA to do something, and less about or data. You can really, I don't care if the number of classes is 3 or 4 or 5. It's just a way to, given our data set, maybe map that to anything you're interested in doing in astrophysics or biophysics or materials physics. And you can think of how PCA can be useful for that. Does that address your question?
Yeah, I mean, I think I understand well. So we have so we got these 3 classes, and then we've got basically, and it's a function of some other variable, right?
Yeah, I imagine there's in this data set, the classes are linked some way to the like they are in to the features. That's one thing that we don't really know in advance. And these are just dummy data, right? But it looks like we can say, given a data set, in this case, it's dummy data, there are apparently some mapping to the features compressed using PCA to the classes. So I would say that is true. But we don't know in advance that's the case. But we can say, looking at this plot here, that must be true just by finding that looks like there's a cluster here and another cluster here, another cluster over here, but they're kind of overlapping in this case.
Okay, so you're saying there's you're essentially trying to identify the trying to identify variables which you don't have in your original data set, right? So by this PCA.
Yeah, I guess you could say that. So in variables meaning a label or some description of the material you're looking at, whether it's ferromagnetic or not, for instance. And you did this and you don't know any y values. So in practice, you don't know the y. This is the point of unsupervised learning. And you might find that your data end up looking like this. And if you don't put labels here, it's kind of a mess. But then maybe you spend your time to label one point over here. You find that it's, say, it's ferromagnet. You label another point over here, and you find that it's antiferromagnet. And over here, it's non-magnetic. And you start getting a sense of, well, maybe there's something about where these things are in this PCA compressed space. It tells you something about their properties. You label another point, and you find that, okay, 2 points over here are ferromagnetic, 2 points over here are what did I say, non-magnetic, 2 points over here, antiferromagnetic. Then you start learning about, well, maybe there's something to this data and their clustering. But I guess in advance, you don't really know that.
Okay, and the hope is that these principal components correspond to something which you can understand.
Yes, yeah, exactly. That it's really the hope.
Okay.
It's really the hope. We don't know in advance that's going to happen, and it might not. In this case, it seems to be happening, but in another case, it might not happen.
Okay.
The idea is you can kind of get a sense of what's going on by making this 2-dimensional plot. But if you're trying to look at your 10-dimensional data, mind you, we put 10 features here, by making plots against first feature, second feature, it might be harder. And there's maybe a lot going on in your 10-dimensional space. You plot one feature versus second feature, first feature versus third feature. Maybe you'll see something interesting, maybe not. But if you can compress the space in some clever way by getting rid of the data that don't have much variance, to focus on data that have the most variance. That's what PCA does. Then you can get a better sense of how to visualize your data. Is there something going on or not? And these are linear transformations. So there could be something going on, but because you have a linear transformation, it doesn't really help you, but it's a good place to start. And even if you don't see any pattern, what you could try to do is use your PCA compressed data set or features as an input to a machine learning model and see if that helps you to make a prediction, especially if it's super high dimensional. Okay. All right, so let me ask you now a question, the royal you. How can the PCA be applied to learn patterns in real world data? So imagine some data that you're working on. It should be high dimensional, so having more than 3 features and maybe a bunch of points. How can this approach kind of help you? Any thoughts? Okay, so don't be shy. So in the interest of time, I'll go back to an earlier question that someone asked. If you had n equals, let's say in this data set, we have, where is it? 300 samples. But let's say this was 1,000 features. You really have 1,000 features is more than 300, much more features than samples. What we could do then, if you want to do machine learning on that, we can do it with 1,000 features and 300 samples. We can compress this to say, 3 or 4 or 5 components, something less than 300, and then try to build a machine learning model using the PCA compressed feature set as opposed to the original feature set. And then we might have a chance of it working. No matter what your data are, you can eventually use this approach to help you build a machine learning model that's going to have some chance of having success. Okay. So let's move on to looking at associated rule learning. Doing on time. Okay, maybe I should go a little faster. So associated rule learning, it's a rule-based ML method for discovering interesting relationships between variables in a large data set. And it basically tries to find rules that exist in the data set. And I'll show you what I mean by that in a second. So it identifies items and rules, association rules between those items, and also item sets, so pairs or triplets of items. Okay, so let's give an example in a few slides. There are different algorithms for doing that. 2 of the most popular ones are this a priori algorithm and the FE growth algorithm. The a priori algorithm, good for small data sets. It's a bit slow. For our purposes, it's perfect. So we'll focus on this one today. It's a priori method. So how does it work? And you identify frequent item sets and generate associated rules from them. This is the language that they use, but it's identifying. Well, I'll just show you an example. That's easier to explain that way. So it creates a support, which is a proportion of materials, for instance, that contain an item or an item set, or portion of data points, you can say, to be more general. The confidence is likelihood that item Y appears given item X is already present. Now again, we'll look at a particular example. This lift measures how much more likely Y appears with X compared to chance. So I think these expressions are more enlightening than the actual definitions here. So support is fraction of times you see X in the data. Confidence is support for X and Y showing at the same time divided by support for X. And lift is confidence over support. And how do you interpret that? If the lift is greater than 1, X and Y are positively correlated. If it's 1, there's no correlation. If it's less than 1, then X and Y are negatively correlated. Okay. So in step 1, you find your frequent item sets. So you scan your data set looking for items that appear many times, given a particular threshold. So if you set your support to be 10%, looking for, say, elements in a materials data set that appears at least 10% of the time, 10% or more. And in step 2, you generate these candidate item sets. So for instance, you combine frequent single elements into pairs. So if your data set contains titanium, oxygen, iron, and nickel, you can create pairs of these titanium, oxygen, iron, oxygen, and so on. In step 3, you start pruning. So you create all these pairs and triplets of item sets. And then you see, well, are there any ones that aren't showing up at all? or not frequently enough, then you get rid of those. So if, for instance, if titanium and oxygen are showing up frequently, you might check for a triplet containing titanium and oxygen. But if titanium and iron aren't very frequent, doesn't show up very often in the data set, then you don't even consider the triplet of titanium and iron something else. In step 4, which is maybe an interesting part, that you look for association rules. And so now, what properties do these pairs or single items share? So for instance, if titanium and oxygen, an example of rule first is an item set containing titanium and oxygen tends to have a high band gap. If that happens 8% of the time, which equals containing titanium and oxygen, then you can say it has a confidence of 80%. If the lift is 1.5, then having both titanium and oxygen tends to increase the likelihood of having a high band gap. That's an example of how it works. So this is a dummy data, but another example, or another 3 examples, if, for instance, your item set has titanium and oxygen, then you might have the rule saying that it has a high band gap with this support, this confidence, and this lift. And iron and oxygen maybe tends to have a low band gap, given the support, confidence, and lift. Okay, confidence is how many times it occurs in the data set. And titanium oxygen maybe has high chemical stability with this much confidence and support. Okay. So if you put that in words, you can say the rule 1 tells you material has titanium and oxygen. There's 80% chance that it has a high band gap. Rule 2 could be contains iron and oxygen. It's more likely to have a low band gap. These are kind of the rules you can develop using this approach. Any questions about this so far?
So these rules are generated by us, the researchers, or do we have an automated way to get some kind of machine learning?
It's a great question.
Yeah.
It's a bit of both. So the rules are kind of generated for you, but you have to give it the right tools, or the right how should I say, components, or the right ingredients. So it's like it'll make the car in the factory, but you have to give it like a seat and a bumper and the wheel for it to kind of make sense. If you give it a wing and a hull of a ship, it can't make a car. Well, I'll give you probably a better example. Actually, before we get to that example, let me try to think of a better one. So if, depending on what you're trying to do, you kind of tune your things you put into the model. So if you're interested in a high band gap or band gap, you want to include band gap as a property in your data set. Of course, if you don't have band gap there, you can't learn band gap. If you interested in oxides, then you need to put oxygen in there. And you need to define what you mean by high and low band gap as well. And in the hands-on example, I think it's going to be clear. So let me walk through that as a means to try to answer your question. Okay. So in this first part here, we are, oh, this is the time where you need to have materials project running. And so hopefully you all have an API key. I'll give you some time to create one if you don't have one, but maybe you can listen to me while you sign up to use materials project. For those of you who have a legacy version, just turn this to be true. If not, if you just creating your key today, you will have be using the legacy version, so keep this to be false. I'm hiding some code here. I'm hiding my API key, but you'll have your API key that you put in this appropriate part of the cell. And then basically you can run this part of the code, and this pulls data from materials product. It pulls materials containing oxygen, selenium, and cerium, information about the band gap if it's greater than 0. And it reports the formula, the elements in the material, the band gap, need of hull, information energy as well. Okay. And this part of the code If you're using the newer version of Materials Project, I think the data are a little bit more difficult to parse than the legacy version. This script helps you to parse those data. So this is just data munging. And in the end, you can go through it if you like, but or ignore it. It's just data munging, basically. In the end, you get a data frame that looks like this, containing the elements, the formula, materials ID from Materials Project, and these labels, information energy, energy above hull, and the band gap. Okay, and so this is answering your question. Depending on what you want to do, you have to kind of put the appropriate information into the model. So let's say we wanted to know something about the band gap, which materials can have low or high band gap. Let's say we're looking for making an ultra high band gap material. And what's the rule for doing that? We have to then think about low band gap, medium band gap, and high band gap by adding a column that has this information. You could do that by creating function categories band gap. You can also do the same thing for information energy using a similar function. And then this code creates these different columns that labels, given this number, is it low, high, medium, given our definition for low, high, medium band gap. Then it adds to those the columns to the data set. And then let's see. It also adds another feature, which is captures the elements from the constituent compound and also creates a column for that. So it'll be 1 if it has iron and 0 if it doesn't have iron, if material containing iron has iron or not. Hopefully that makes sense. And if you do some parsing, you get another data set looking like this. Here's what I meant by if it contains, say, oxygen or not. Doesn't contain, these materials won't contain lead, for instance, this with the 0 here. And I've added here my columns for this information energy high, low, medium. These are describing that information. And with this information, then you pass it into the model, and then it creates the rules for you. So this is what I meant by you have to give it the right ingredients for it to create the thing you want to create. If you didn't put something about high, low, medium band gap, it can't create a rule for you to do that, if that makes sense. You need to also set some minimum supports when you're creating the rule sets. And then the rest of it is calculating the rules. It's pretty easy to do. It's a couple lines. And then you can plot the results or print the results. Hang on, I'm having some technical difficulties here. By the way, it's also useful to kind of just plot your data. In this example, I'm plotting histogram of my information energy data, which is a nice thing to always do to get a sense of what's going on in your data set. Okay, so then I call this function association rules, given the right information, and it creates the rules for me. And let's look at an example of what that means. So we can print the rules and print the data frame containing the rules. And there's antecedents. So this is the before the arrow and the consequence after the arrow. Imagine the arrow in this mapping here to here. And so what this means, these aren't the cleanest looking set of rules, but this is what we get from the analysis. This says if you have an iodine containing silicon and sulfur, then you tend to have a medium stability. And then interpreting oxygen and sodium, it's not super clear how to do that. But I think when I did this, they're more easily interpreted rules that you can find in this data frame. So please sift through more than just these rows. There's 158 to kind of inspect. Maybe you could find some more easily interpretable rules. Issue with is that they're not always easily interpretable. Okay. So I'll give you some time to go through that on your own, evaluate cells, that makes sense what's going on, inspect this data frame, looking at other rules that could pop up. And then there's some questions. Can these rules be easily interpreted? It goes back to your question earlier. How do we create the rule sets? Maybe there's a better way of doing this. You have to include the elements. You have to set the support correctly. There's one issue with support is, I'll ask you maybe in a few minutes what that issue is. It's linked to the data set you have access to. And how do you improve in data interpretability? And I'm asking you to consider the data distribution and the choice of descriptors, which is super important for doing this, getting meaning from this. Okay, so have a go, and I'll stop in about 3 minutes to ask you some questions. If you get stuck, feel free to ask a question in the chat, or just unmute your mic and ask. Okay, so I think we're at time. So let me ask you, can these results be easily interpreted? Or did you find one that could be? Okay, so I said these are a little challenging to interpret. And I was looking for one that can, but code is taking some time to complete here. Let's see. What about the data distribution? So let's say if you're looking at a data set for, let's say, chemical stability, and you only have materials containing unstable compounds for some by some metric, do you think you'll learn a good rule that learns materials that have stability, that have high chemical stability. Well, no. So if you have a data set with materials with low chemical stability, looking for with materials with high chemical stability, you don't have any have enough of those data. You can't develop that rule with high enough confidence. So your rule set really is highly dependent on the data that you have access to. I need to be sufficiently diverse to get you your rule with any reliability. Does that make sense? Okay, hopefully it does. So let's move on and look at generative modeling, which is pretty exciting. Okay. So generative models, these are models that learn an underlying data distribution, creates new samples, or in our case, predicts new materials that maybe don't exist in any database yet, as opposed to discriminative models, which ones that predict labels, either a class or a particular value. And examples of generative models include VAEs, variational autoencoders, GANs, diffusion models, and the output is new materials as opposed to just labels or class probabilities for discriminative models. There are maybe 3 broad classes of generative models: probabilistic generative models, deep learning based ones, and also transformer based ones. You all probably have used transformer based ones by using ChatGPT. For deep learning ones, you basically take a neural network, which learns some complex data distribution. And particularly, you use a variation autoencoder, which codes data into latent space and reconstructs it. This often is used in drug discovery, material discovery. These are GANs, or generative adversarial networks. They're used for image analysis and molecular molecule generation. They're typically tough to train and work with, so we'll focus on VAEs for this tutorial. And diffusion models, which are models that add noise data and then denoise the data, and those have been successfully used to generate novel molecules and crystal structures. They're kind of clever algorithm. We'll touch on transformer-based models just a little bit because you've all probably used ChatGPT. This is the kind of the algorithm used or framework used by ChatGPT, this generative pre-trained transformer model. Okay, for VAEs, these are typically similar to an autoencoder. This is kind of a simpler version of a variational encoder. This is the architecture for an autoencoder shown here, where you, for instance, for images, you have an input image here. You encode image to some smaller dimensional latent space. So let's say this is a 1,000 pixels. This is like a 10, and you decode it back into 1,000 pixels. So it's a bit like an MP3 or a JPEG. You do compression for audio or images. But in this case, arbitrary data sets could be an image, could be something describing materials data. You can compress it into a smaller dimensional latent space. So it could be a dimensionality reduction tool, but we'll use it for generative modeling. We can't do that really with autoencoder. But what we can do to tweak it is to do a variational autoencoder approach. And the tweak is to create a probability distribution in the latent space instead of just a data point. And with the distribution of probabilities, what you could do is you could start sampling the distribution and then reconstruct that sample value in latent space. And that facilitates generating new data, which is actually kind of neat. So you add the mean and variance of a Gaussian distribution, which facilitates your creating a distribution of data in a latent space. And you add a KL divergence, which is trying to get your distributions to match up, and also your typical MAC mean squared error reconstruction loss. Okay, so the VAE introduces a probabilistic element to the encoding process. Again, you model this as a Gaussian distribution with mean and variance sigma squared. And again, it uses the scale, which is a Kullback-Leibler divergence, to help make your data set, your latent space, rather continuous and well structured. Also reduces overfitting. Okay, now we get to enjoy a hands-on example. Little time to spare. before we have to close in about 20 minutes. No, 15 minutes or so. Let's turn to that. Yeah, hands-on example. By going to the generative modeling part of the Google Colab notebook, keep installing necessary packages. We'll use, again, the materials product to get some data for us. Run this cell. And we'll have some data munging done in this cell, pulling the dictionary downloaded from materials product and creating a nice data frame from that. We'll get something looking like this. Formula, some elements, information engine, and band gap. Then to do our input to our variation autoencoder, we'll just get some description that is the one hot encoded whether this atom element exists in the compound or not. This is code for doing that. In the end, we get something like this, which, does the element or compound contain titanium or not, or silver or not, aluminum or not, and so on. So we get this very nice 87 dimension vector, which is encoding or material. You could think, is this the best encoding for material? You might be thinking no, but this is a nice example to play with for making things more sophisticated and then useful. All right, the next bit of code, you build your autoencoder in a few lines using Keras, which is quite nice. If you look at the code, you may notice the autoencoder is not symmetric. You can ask me why later if we have time. This is the bit that creates the probability distribution and sampling. And so in this part of the code, you create the encoder and then the decoder. You can inspect it by printing model. And then what you can do is you can put everything together into variation autoencoder by coupling the encoder to the decoder, finding the loss function, calling the function, and fitting to the data. And here I only fit over 5 epochs just for the toy example. You can please increase this and use GPUs. You can also play with a batch size to get a better fit, which I don't really get a good fit in 5 epochs. That's okay for the example. So hopefully you've run that while I was talking. I'll give you a few minutes to maybe change the number of hidden layers a bit, run for a bit longer, maybe instead of 5 epochs, run for 50 epochs. This is completely the first time to do this. It's hard to cover everything in any great detail, but use this as an opportunity to say, well, what's a bit batch size? What does that do? If I play with that, what happens? And you can look it up on Google. It's just essentially the number of points you look at to do gradient descent. If you haven't heard of gradient descent before, it's completely fine. It's a good time, gives you a good direction to learn how to learn all the vernacular involved. So I'll give you a few minutes to play with the hyperparameters, activation functions. So you might want to, for instance, change this ReLU to something else. This is an activation function. This it has this kind of shape. It's a rectified linear unit. You can change it to something else like CILU or ALU, or do a tanch. Don't do sigmoid. Try linear and see what happens. You could try adding another hidden layer in the encoder. If you like. And please ask if you have some questions. And if this is completely new, building a neural network, no problem. Your homework is to go and understand each line, given this as a starting point. If you have some experience, then probably you'll have some questions. If not, you can definitely go and learn about these things later and play with things and see how you can get the model to improve. What do you do to get it to break, and so on. Lots of things to change. One thing you can keep track of is the loss. So it's typically starts high and gets slower. You can even plot the loss as a function of the number of epochs. which is a good thing to do, which I actually haven't done, but you should actually always do that. Okay, so hopefully you had a chance to play with that a bit. I'll move on a little bit faster than I maybe should for the next part, which is generating new materials. So this is, I think, the really cool part. So after you construct your model, if you 5e blocks, it's not going to be a really good model, so you should run it for longer if you have the time. And you can then sample the latent space, that is this probability distribution. And we do this in this line. And we can do a prediction of the sample latest space using the decoder. Then we can inverse transform. What we did before was scale the input space. We kind of unscale it. Then we can then plot the results in this data frame. So this says there's some fraction of this new material containing this element, this element, this element, so on. You might notice that there's lots of small fractions of many elements. So can this become more reasonable if you train it for longer? Is this a reasonable representation to start with? It's a good toy example to play with, but maybe not the best representation. For instance, it doesn't have crystal structure included at all. So how do you include crystal structure to decode a material that has also the crystal structure in it? There are some ways you can think about doing that, which we can discuss. We'll have a few minutes to have some discussion. So each row represents a synthetic material composition that doesn't exist in any database. The values for each element indicate its presence in the new material. And you have also the information energy per atom, which provides an estimate for the chemical stability of the material. I'll give you a couple minutes to kind of look through that, digest what's going on before I ask a couple questions. Then we have to wrap up pretty soon. Are there any questions?
Is there any way we could tell if these generated materials can be fabricated in real life?
That's a wonderful
Sure.
question. That's a
Oh,
beautiful question. It's kind of the cutting edge of research to actually predict whether it can be fabricated in real life. There are some first principles calculations checks you can do. So let's say if we added some information about a crystal structure, when we output a crystal structure, so we have chemical composition and crystal structure, we could then do density functional theory to check is the information energy match what we predicted? Is it dynamically stable? We can then look for competing phases. And if we found all those to agree with what we kind of expect from material that exists in the lab, then we can say to our synthesis friends, can you try to make this? But right now, there's no guarantee. I think Google and a group, Berkeley, came out. My memory is horrible, so don't quote me on it. I know this is being recorded. With a paper a couple of years ago, I think now, which claimed to do this, and there is some controversy with how successful it is. I won't get into the controversy, but let's just say that it's a kind of active area of research. And fantastic question. So far, we're predicting new materials, and I wouldn't trust this particular algorithm. You need to include, for instance, crystal structure, but you have maybe some chemical compositions. If you train it well enough, maybe it'll be a reasonable set of chemical compositions, but we haven't said anything really about is it synthesizable or not. That's another level of complexity.
so when you're mentioning the crystal structure, are you saying that that should be incorporated in the input?
Yeah,
Or
absolutely.
is there
In the input, I think in this architecture, it's easy to put in the input. So far, we're just told the model that it has these elements in it. We haven't said, well, how are the elements arranged? What structure are they arranged in? And for this toy example, it's perfect example for pedagogical reasons, but not the best for actually doing research. So, but it gives you a starting point to then go ahead and add cluster structure somehow, maybe by looking at the atomic positions and putting it there, and then as an input, then having it learn how to make the positions match to the output. Then your latent space has encoded also the crystal structure, which you could then use to decode some potentially new materials. And this is not the first time this has been done. People have done this in research with varying degrees of success. Okay, so I think we're getting close to the 9-minute time. So let me kind of wrap up the notebook. Thanks for the questions. What you can do is then visualize your latent space using tsne, which is a nonlinear data visualization tool. And it looks like this. And you can try to look for patterns in data by inspecting latent space. Now, my latent space isn't that good in this example because I only trained for 5 epochs. If you run yours for longer, you might see that there's more reasonable patterns forming. You can then do PCA as well, tools we talked about earlier, and maybe find better clusters in your PCA of your latent space. And then kind of research challenge, which I think I'll tell you about, and then go back to the presentation for the last 2 minutes or so. This is a homework for you. You don't have time to do it here. You would basically try to reproduce results or use results created in a previous paper. You can see the links here. And then this didn't work super well, but you can mount your data and then create a data frame given the CSV file that's linked to this paper. And then select some descriptors that are provided in the article. Then look for patterns in this data using the tools we did today, PCA, tsne, k-means clustering. Think about what tools, how you can apply the tools you learned today to look for patterns in those data you have. And this is really an active area of research, but this is probably actually something I want to do, which I haven't done yet. So if you find something cool, please let me know. We can maybe collaborate on something together. All right. And the rest of this is just basically things to do for your homework, which we won't have time to do right now. Okay, so let's go back to the lecture. So to summarize, we found that unsupervised learning can help identify patterns in the data. We looked at the difference between supervised learning and unsupervised learning. We looked in particular at k-means clustering, PCA. We used this a priori associated rule learning. We looked a little bit also at the variational autoencoders, which is really cool and good for creating new data, potentially new materials if it's done correctly. Outlook, you can actually do something like semi-supervised learning or self-supervised learning, which is combining unsupervised learning, supervised learning. Which is pretty cool. We don't have time to talk about it yet or here today, but if you want to learn more paper on this, you can access paper using this QR code and read more about that. I think it's pretty exciting. It's exciting direction. I think people are beginning to take more advantage of. And again, for your homework, it's described looking at the data set that's created in this paper that you can find in the notebook, and also references down here, which you can use tools you learned today to really do research. And again, if you find something cool, please let me know, because this is something actually I want to do that I haven't done yet for a research level problem. Right, so you want more information, please visit my website, materials-informatics.com. There's also a GDS webinar series on YouTube, including the rest of these tutorials. You can look at Java's tutorials at NIST. And I started with Andrew Ng's machine learning course on Coursera. It's a fantastic course, a good place to get started with machine learning. And we're interested in hiring talented students. If you're interested in working in this materials informatics space, please consider applying to RPI. And last but not least, this is a haiku I created using ChatGPT. It's a way we can create poems using generative modeling. And this one the prompt is create a haiku for unsupervised learning for materials informatics. And it goes, patterns emerge free, atoms whisper their secrets, no guide yet they learn. Thank you for your attention. Any last questions? Hey, Julie, why don't you take over?